Okay, so we have a board ready. What do we want to talk about? Yep.
Can you do number 2 on fall 2016?
Number 2, fall 2016. Let's go here. Whoa, that is a big head. Where did that come out? Alright, let's see here. Okay, that's better. Say it again, fall
2016,
16?
yeah, number
Like-
2.
exam number 1.
Yes. Thank you.
And then we'll move this over to. Problem number 2.
Yes, please. Yeah.
Okay, so we have this induction machine of problem 1 that has a capacitor bank connected to the machine as shown in the diagram. Notice that the feeder inductance has been removed, okay? And the induction machine parameters are given. So it's a 3-phase 60 Hertz machine. This is the rated power and the voltage line to line. And we're given the power factor at this rated voltage. So the machine is operating at 100 kilowatts, 0.8 lagging, so I can find S pretty easily. And then I want to find this capacitance of the capacitor. So that the 3-phase source supplies power at unity power factor. So we always like to draw our equivalent circuit for these problems. So we'll start with that. So I have 3 elements, right? I don't care about if this is a Y or a delta. Right now I don't care about if this is a Y or a delta, because I'll just find the Y equivalent capacitance or per phase capacitance, and then I can consider if it's a delta or a Y at the very end. And then I just have a source again. I don't care if it's a Y or a delta. But I have 3 elements in here. Let's do this. I have 3 elements in here. It's gonna be the machine that I don't actually know the impedance of. I'll call it ZM for machine. This will be V, let's call it in, and this will be some. Let's for now find the impedance of the capacitor or the reactance of the capacitor, and then we'll find the actual capacitor value. So that's my equivalent circuit, and I am trying to play around with the capacitance to find unity power factor. So probably the best approach is to look at power in this problem, right? Because we have quite a bit of information given in the power domain here. So right away we can say that P motor is 100 kilowatts. I actually already know this voltage and this voltage because I know what Vn is. And from the power, or the apparent power, I could also find the current. But maybe in this problem I don't even need to do that. So since I know Pm, I can find, really what I want to find is the apparent power, right? Why? Because I want to find the real and the reactive power that's consumed by the motor so that I can compensate it by the capacitor. So S magnitude, anybody help me out, what will that be for this problem?
Well, would you use magnitude and not that actual, like, for S?
Well, I could find S phasor 2. Sorry, S phasor 2. Let's write out what it is. This is a good thing to have.
This magnitude would be 100 kilowatts over the power factor of 0.8.
Absolutely, yep. That's so the magnitude will be P divided by power factor. Or I could write out this equation for S. S will be S magnitude times cosine of theta plus S magnitude sine of theta. And this here, of course, is the power factor. And I'm missing a J here, right? So if I wanted to use this equation here, that would be the easiest way to do that would be to find theta, right? So I can say power factor is cosine of theta. So theta will be cosine inverse power factor, right? And I believe then theta should be about 36.8 degrees or something like that. If someone can check, that would be great. What I do know by heart is that for a power factor that if sine of theta is 0.8, sorry, if cosine of theta is 0.8, sine of theta will be 0.6. And I just happen to have that memorized, but from here I can basically solve for S. S will be the 100 kilowatts, which, and then I have plus or minus. This is a motor that's inductive. Is the Q positive or negative for an inductive system?
Positive.
Q is positive, right? So I have plus J 100 divided by 0.8, which was my S, right? From this equation over here. That's S magnitude times the sine theta, which is 0.6. So this here was S magnitude. And this was 100 divided by 0.8 multiplied by 0.8, which is 100, of course, right?
Wait, isn't the magnitude of S 125? Because power divided by power factor would be 100 kilowatts divided by 0.8, right?
It is. So S magnitude, yep, is 100 divided by 0.8.
Oh, okay.
Yep.
Sorry.
This whole thing. So I have S now. I can even draw my power triangle. It'll be positive. This will be P, Q, and S. And the values I think is 100 we said. Q was
75.
help me out, what is it?
75 kilowatts.
75 and S was 125?
Yeah.
And then what am I trying to do in this problem is I need to find Q capacitor such that power factor equals to 1. So I know right away what is the total capacitance, total reactive power supplied by all three capacitors, right? Anybody help me out? What number is that?
77.
It's gonna be the 75, yeah. So this will be QC is 75, and I'll put units here. VA reactive, kilowatts, or watts, I'm sorry. Let me double check that. Are we talking about watts or kilowatts? Kilowatts. So I'll put a K here, K here, K here. It doesn't matter as long as I am consistent. Okay,
Wait,
so
why,
this
why
is.
is that QC?
I'm sorry, say it again.
Why is that QC? Why is it 75K?
Why is it 75K? Because
All of the reactive power is coming from the capacitor bank.
Oh,
So-
because I thought you were finding S of this is S of the machine.
it is, so this is S of the machine, S of the machine, S of the machine. Now what I want to do with the capacitor is bring the power factor of the combined system
Okay.
to unity. So I want this cap basically to cancel out the reactive, the reactive component of that
Okay.
machine.
Okay. Got it.
So that new S of, this will be S of machine plus capacitor will be purely real. So S will be the same as P for the
Okay.
new system.
Got it.
So I found QC. QC now is 75 kV reactive. Kilobars.
Why do we not say that it's negative to cancel out the Q from before?
You're absolutely right, there should be a minus here. Yep. There should be a minus here, yep, this is minus. And then what we're trying to do is we're saying that these guys are Y connected. So since I'm trying to find, XC here, I know what the total reactive power of the three capacitors is. To find the actual capacitor value, I will use my formula. Q is I squared XC, or in this case it'll be easier to use Q is V squared over XC. So I need to figure out what V I have over the cap. So I'm given, if I go back to here, I'm given the V of the motor is this value here. This is my source voltage. I'll write that out over here. V in line to line is 480 volts. And I'll just deal with the magnitudes here to begin with. Of course, then I can use the phasors down the line if needed. But if I just look at the magnitude of V in, it'll be of course the 480 by square root of 3. And I don't really care about the fact that this is shifted by 30 degrees from this guy at this point, because I haven't really defined a reference phasor just yet. So it only becomes relevant when I start, when I determine what is my reference phasor. So in this particular problem, I know what this voltage is. I don't know the phase angle, but we said always, let's make the per phase voltage source be my reference. Again, I can define whatever I want. Let's pick that. So let's set V in per phase as the reference. So V in phasor now will be 277 angle 0 volts. 277 is 480 by square root of 3. And so now I know this voltage from this simple equivalent circuit. I can see that that's actually the voltage over XC as well. And from there I can find the value of XC. Going back here, this is QC. So note that this is the total cap, let me add three-phase cap bank reactive power. So to find XC, we said we'll take QC per phase, and we'll set that equal to V in per phase, magnitude squared, divided by XC, right? And in our case, QC per phase will be the 75 kilowatts divided by 3, and that will be equal to V in per phase, that's 277 squared, divided by XC. So I can solve for XC from there. Again, I divided here by 3 because I'm looking at per phase. 75 was for the three-phase cap bank. We know that each capacitor in each phase will consume the same amount of power because they are balanced. They have the same voltage and the same capacitance value in all cases. So I can find, so that's where this comes from. We found V per phase. I only need the magnitude, even though the phase is 0 anyway. And then I can find XC from there.
Isn't it conjugate? XC conjugate?
In this case, remember XC is just the reactance of the capacitor.
Okay.
So if where we use the conjugate was we had V in divided by XC, that was our current, multiplied by V in complex conjugate, that would give me S.
Oh, okay.
In this case, I'm only looking at the Q component, but still the even in that case, what I end up with, we can derive that very quickly. If I look at S complex conjugate, it is V times I complex conjugate, which is V complex conjugate, Z complex conjugate, which is equal to V squared over Z complex conjugate. But in this case, Z is equal to XC, i.e. there is no real component. So this equation is dangerous to use if I have a Z down here. In other words, if I have two elements in series, you have to be careful because I'm going to have a complex number here, and then yeah, I can still use this equation, but I have to be careful about the signs of Z complex conjugate. In this case, I've already taken care of that because there's no real component. This is just a constant. This is not a complex number, right? This I've extracted essentially just the second term here. So I have V squared X, let's call it plus R. And then I can find the real and reactive component here. So what I'll end up with is, if I multiply this by R minus JX over R minus JX, I'll end up with S is V squared R over R squared plus X squared minus J V squared X over so in our case, so this is pretty involved, but what we're looking at in this part of the problem is just this term. And this term becomes a lot simpler because R is 0. X squared cancels this X, so I get V squared over X. And I don't have to worry about, I'm just looking at this magnitude. And I am comparing it to the value of Q. So that's why the complex conjugate doesn't show up here, is because we're only looking at this term. And that's why I didn't even care about the sign, because I knew I'll end up with a capacitance that should be always positive, right? So I completely ignored the complex conjugate in this particular case. So again, when I have two elements in series, if I'm applying this equation, it gets a little bit tricky. Usually when I have two elements in series, it becomes easier to deal with Z multiplied by I squared.
Yeah, okay.
When I have two elements in series.
Okay.
Go ahead, somebody had.
Yeah, I was just wondering if you'd like, so you want the Q to be negative, right? Because I know you ignored it, but if you didn't, under the 277 squared, if you said that is Z conjugate, is it just negative XC? Because the R would be 0. Does that make sense? Right.
Yeah, I could have had, like we talked about, we ended up with a negative sign here.
Yeah.
if I could have put a minus here and a minus here. But even if I made a mistake here, and somehow I forgot, let's say this minus here, I should always know that XC will be capacitive
Yeah.
because my initial, well, the problem statement says I'm looking for a capacitor, right? And my initial power factor was lagging, right? So I'm trying to improve it by adding something that's leading or capacitive. And then I can't have a negative capacitance, right? When I end up, at the end of the day, we're trying to find XC, which is 1 over omega C. So once I find that C per phase or CY connected, that capacitor must be a positive value. So this is, let me move this again. This is kind of a side note. And we'll call it here, side note. And then getting back to our problem, from here we can solve for XC, which is 1 over omega C. And then, which is basically 1 over 370. Well, let me double check. What's the frequency here? Frequency is given at 60 hertz, so it is 377. 2 pi 60 is 377 times C. So this is C per phase, right? So this is C per phase, since we used the line to neutral voltage in this equation. Right, so I looked at the voltage in the per phase equivalent. I did all my analysis on the per phase equivalent. And per phase, of course, equals to Y connected. So how would I find the delta equivalent of this capacitor?
We should divide by 3.
That's a tricky one, right? Yes, you're absolutely right.
Okay.
So XC would be multiplied by 3, but the capacitance would end up being divided by 3. So you're right.
Oh, okay, yeah, I didn't think of that, but I guess so.
Another way to think about it is, the simplest way I could do that is I could actually have used the 480 here. If I used 480 here, that's basically 277 times square root of 3. Why am I using 480? Because that's the voltage that would be applied over that capacitor. I should always do my analysis on the per phase equivalent. But let's write that out too. So not to confuse things, it's always best to follow an algorithm. So we had that ZY connected is, or 3ZY is 1 Z delta. Z delta should be larger. The delta impedance is always larger. So 3 times ZY is Z delta. So that implies if I was to find the delta connected capacitance, I would take XC delta equals xc y times 3 using this equation here. And from there I could find c delta will be or write this out.
Wait, isn't
X
it?
c delta would then be equal to 1 over omega c delta. Yep.
Is it not 3z delta is equal to zy, or? Cause
The way I remember it is the delta impedance should be larger than the y impedance. And I have to look at impedance, whatever is in ohms, not in farads or henries. So I have to work with impedance in ohms, and I know that the impedance of the delta should be larger than the y.
Okay.
So the 3 should be here. Yep.
For this 3 times change with the delta y configuration, so this is valid for impedance but it's not valid for voltage sources, correct?
For the voltage sources, it is not correct, absolutely. So when we go from if we look at our cheat sheet, as we go from a y to a delta, the delta will be 3 times larger than the y. But when we go from a line to neutral, or from a line to neutral, I'll multiply by square root of 3 and phase shift by 30. Yep. So it's different for the impedance versus voltages and currents. Yep. And we have a derivation of how that all works out in the notes. But the end result is what you see here. Since you don't want to be deriving that every time, we need some kind of a shorthand like this. Yep.
Where can we access the cheat sheet? Is it on the Moodle course?
It's on Moodle. Yep. I think it has some name like 3-phase summary. Yeah.
Thank you.
And that'll be provided with the inclusion of the couple of equations we added in class on yesterday. Okay, any other problems we want to go through? Yep.
I have a question about this one. So for when we're finding capacitance, I thought that we were supposed to use impedance is equal to like negative J over omega C for a capacitor. Why are we able to use reactance for this?
Say that again.
So I thought when we were finding capacitance,
Yep.
like for based on like a reactive power, I thought we would use impedance. Like isn't reactance like the inverse? Hang on, impedance is like the inverse of reactance, correct?
Impedance so we have impedance, which has a real resistive and a reactive component. Yep.
Oh, it's because there's only a reactive component.
There's only
Oh.
in
Okay.
this problem.
That makes
There's
sense.
only a reactive component. There's no. Yep.
Okay.
We're not. I see your point. We're not using Z, the impedance. We're using the reactance directly because we know there's no resistive component in this problem.
Okay. That
Yep.
makes more sense. Thank you.
Yep.
What is the answer for this?
What is the answer? Good question. We did not solve for that. Let's do it very quickly. Somebody needs to help me out here. So XC is
That is what I got as well.
277 squared times 3 divided by 750,000. So make sure I got that right. Yep. So anybody has a calculator handy?
863.5 microfarads.
wait, that
Well, that value.
Well, for the final
The
answer.
final answer, yeah, so. I don't know if I-
Oh, I'm sorry.
Jumped
That's
to that conclusion, but,
you
yeah.
jumped a step there. Okay, perfect. Let me move that over.
For that, you get 3.0 3.069.
Say it again?
3.069.
3.069. And that'll be in ohms, right?
Yeah. So what
Okay.
you were saying for this question, when we're talking about like between Y and delta, so for this question it's asking for Y, but you were basically just saying if it did ask for delta, we would basically divide the capacitance we got for the Y connected by 3.
That's what it ends up being,
Okay.
but we skipped a bunch of steps. So it's always best to follow the right steps that we have laid out. So we found the ZY.
Yeah.
To find the Z delta, we multiply the ZY by 3. Once we find Z delta, which in our case is X delta, there's no real component. So XC delta, I rewrote this equation over here as it applies in our case where there's no R. So XC delta will be 3 XCY, and then XC delta is 1 over omega C delta. If you skip a bunch of steps, it turns out that the C delta should be 3 times smaller than this value.
Okay.
So about 300 micro or so, a little bit less, yep.
So my main concern with this test is time. Like I feel like this all makes sense, but I'm a bit worried just with all the complex math and such that, I mean, these problems are pretty involved. Do you anticipate time being a major factor, or do you think we'll mostly be able to have enough time?
If you're deep into complex calculations, you're probably on the wrong track. If we look at some of these problems, like for example, there were some 3-phase problems where you had a bunch of elements in series and a bunch of elements in parallel. I won't give you any problems like that. It will be the circuits will be very simple. So I don't foresee that we'll have an issue with time.
Okay, that's a relief. And I know, I guess it's probably too soon in the test to change it, but Dr. White apparently used to do take-home tests. Have you considered that? I mean, I know typically you're not supposed to assign that kind of thing over break, but I don't think anybody would complain.
I'm not a fan of take-homes. Yeah. There's evidence that testing is the best way to learn, and there's many studies that show that, surprisingly, that you should test yourself often and right before you learn the material. So homeworks are really helpful, but actually doing the test, there'll be a lot of learning there.
Okay,
These questions are a little, I think for this class, this is a really a class that is well suited for in-class exams. And like I said, I'm expecting people to start leaving at least 20 minutes before the end.
Okay, well that's great to hear.
Yeah. Yeah, don't leave 20 minutes before the end though, it's always good to check your work. I expect you to be done 20 minutes before the end. With the first pass. Okay, should we go ahead and do another problem? Yep.
Sorry, there was actually just one more I had. So with the single phase, I imagine the test will mostly be 3-phase, but there were some, on the homework 1, the optional one, there were some RMS calculations that were with some kind of strange waves. Are we going to be doing like RMS integration on here?
No. There will be no problems trying to find the average and RMS values of non-sinusoidal waveforms. Yeah.
Okay, great, thank you.
So we'll jump right into single and 3-phase AC circuit analysis. Yeah. Yeah, one of the sample exams had a problem that looked at a square waveform. There won't be a problem like that. Yep.
So for fall 2015, I know you mentioned like a bunch of series and parallel stuff is not gonna be like that. So problem 2 in fall 2015, is that something we would not be seeing on the exam? Just because those are a little bit more involved.
Like this one, for example. This I think is reasonable because really what we have here is two elements, right? A voltage source and two elements, similar to the problem we just did.
Right.
Then there was another problem that had like a couple of additional impedances, and you shouldn't expect anything that complicated. Also note that all your values will typically simplify to some round numbers, both on the input voltage and the impedances, so the algebra should be pretty simple. Even could be done by hand in some cases. Yep.
On that same test, for number 1, when you're drawing the per phase equivalent, would the inductor be in series or parallel to the load or the ZIL?
In this problem 1 here,
Yeah, for letter B.
so this is the problem statement. So we have, this is our problem that we looked at. The machine is connected to a 3-phase source through a feeder. So all we have is the induction machine, a voltage source, and this feeder. And we're looking for the per phase equivalent. What that would look like is we have the voltage source. So if I try to draw kind of a block diagram of the 3-phase system, and I need to move to, let me move to a different tool here. If I looked at a drawing of the whole system, it would look like this. I have a voltage source, then I have an impedance, and then I have a machine. I call it induction machine for short. The question is to draw the per phase equivalent circuit. So the equivalent circuit would be that voltage source. I have the line impedance, only one shows up in the per phase equivalent, and then I'll have some impedance of the induction machine. This will be, here I'm given the inductance of this L is 27 Henry, I believe, millihenry, 0.20. Well, that's actually the same thing. 27 micro Henry. So 0.27 Henry. And from there I can find this is XL. This is 0.10, same thing. And then in this case I found the impedance of the induction machine complex. It ended up being this value here. So that would be that per phase equivalent circuit.
Okay.
And here we have find the per phase equivalent impedance of the induction machine. So I use this equation that S is really the equation we have is S is V squared over Z complex conjugate, or if I'm looking for Z, it'll be this equation here, V squared over S complex conjugate. I can move the complex conjugate back and forth here. Or I could just find Z complex conjugate and then change the sign to find the Z. Or, and then very important point, if you get all bogged up with these signs, you know you're finding the impedance of the induction machine. You're given that this is the power factor of the induction machine. So I should know that this should be positive because I should end up with an inductor at the end of the day, not with a capacitor. So if you end up with a minus here, you know you're off. So it's always good to kind of do a sanity check with your result, right? So lagging power factor, the reactive component or the imaginary component of the impedance will be positive, and the current will be lagging the voltage, right? Okay, any other problems we want to go through? This one has a solution, so it might not be that interesting. That's the only one that was useful here. This is kind of similar to some of the parts we did earlier. Any questions about this one? So here you're given this reference phasor, so right away I can tell that VAN will be 277 angle 0. And then I can draw my per phase equivalent, which will be that source of 277 angle 0. And then I have one impedance here, CY, which is already given. And then this will be Z delta divided by 3. So in this problem I have, again the math should be easy, 10 plus J5, and this will be 10 minus J5. Yep.
I've got well, I wouldn't like to go over the whole thing because that would take like 2 hours, but problem 5 on homework 3, the problem I had was, I was looking through the solutions that were provided by WebAssign, and at one point, it wasn't requested in the question, but to calculate another value, we found the current going through the motor, which was found to be, in my example, 14.47, and then later we're asked to find the current going through what should be that same section of wire, and now it is, let's see, 13.52. So just like close, but not the same, and I'm wondering how it happened that in that same loop of wire, we had 2 different currents found on the solution. Maybe there's just something obvious I'm missing, but it seems odd.
Trying to get this, this is homework 3, right?
Yes.
Just trying to get let's get the problem statement up here at least. This one here.
It was problem 5.
Oh, I'm sorry. This one here.
Yes.
And
if you're able to pull up the solutions, I think it'd be easier to show you what I'm referring to. Yeah, that blue underlines.
Okay.
Yes, so is there that I motor that's found, that 14.29,
Okay.
and then that IS later in part B as 13.6. How could those be different?
Okay.
But there is no, it's not connected at part B, unless I misread that,
So we have a three-phase voltage source.
because it's only in question 6. When you can,
Used to supply a three-phase motor through a distribution feeder cable. Let's see if I can make this whole thing a little bit bigger. So three-phase voltage source, supplying a three-phase motor through a distribution feeder. We're giving circuit values, V rated. This is the voltage source line to line. So for this per phase equivalent, I would divide this by square root of 3. Power is given always as a three-phase value, so the power and the power factor are given for the motor. Oh, this is the rating of the motor, sorry. So this is the power and the power factor of the motor. And I can find this R motor and L motor, which I think was asked for in the problem, as V squared over P will give me the R, and then V squared, not true. I have to be careful, right? So a better way to do that is I could take I could find the Q. Sorry, I could find fairly easily, I could find S. So this is P, and we just did that, we could find the Q, and therefore the S. And then from the S, I could take V, which is known, and find the current in this motor. Then from there I could find the R and the L. I think no one had the problem with that. Z line is given. I don't have to change anything other than multiply by 2.6. So this is given. You can find this fairly easily. So the following is per phase equivalent circuit for this problem. Determine the VSP.
yeah, the main thing is just because part D in number 6 says this shunt is introduced. So
Yeah.
assuming that's not yet connected, how
Yeah, for
is
this-
it that the motor current and the source current are different?
Okay, let's see. Yep. So we found all of these things. Further assume that the motor can be modeled as a constant. Okay. Series impedance. Okay, so these values don't change, and we want to find the impedance of the cable we talked about in the motor. So part A is pretty straightforward. Then part B, calculate the motor load line to line voltage and line current. So the motor, so for part B, we would find this current, so this is not in there, fairly simple circuit analysis. First thing I would do is find the current, which is V divided by this total impedance. So I could find the current, and then that current multiplied by this voltage will give me the voltage across the motor. That'll give me the line to neutral voltage. I multiply that by square root of 3, phase shifted by 30 degrees to get the line to line voltage across the motor. So I think that's all okay. So that'll be I feeder, which was the current in the per phase equivalent. So, and then if this is line to line, we talked about that just a second ago. Okay, part C, we want to find part C, calculate the apparent power supplied by the voltage source and the feeder line loss. Apparent power supplied by the voltage source and the feeder line loss. apparent power from the source, we know the voltage, we know the current. V times I complex conjugate will be the apparent power complex, and if I take its magnitude, that's what I'm looking for here, just the magnitude. Then P loss feeder is always I squared R. I already know the feeder current squared multiplied by the resistor.
Yeah.
Okay.
I think from this point, I'm all set. Thank you. I mean, this is a pretty tough one.
But then the problem, so the question was, why are these two different?
Yes. I moat and IS.
Yeah, they should not be different because the capacitor has not been introduced. So how are they different? That is a good question.
I think one of them is line to line, because it's being divided by square root of 3.
You're right, this is, because the motor
Well, they're both
is
line.
delta connected.
And I think IS is line to neutral. Or,
Yeah, somewhere in the problem it says, let's make sure that's true.
Yes.
Oh, okay.
It's a three-phase motor.
It does not say that the motor is delta connected.
Well, but they're too close to be off by root 3.
They should be off by a root of 3, absolutely.
It's a
Yeah.
delta connected generator.
They're nowhere near off by root 3.
Yeah.
One uses the rated voltage and the other uses the source
Oh.
phase voltage.
Okay. So like,
So I showed it, I don't know why, it's just that's what the calculation is.
They're way off to be a calculation error. And they're too close to be a square root of 3.
the rated, we found the source from the rated voltage.
were we asked? I know.
So let's look here. How do we find this I motor? We took, I know what's going on. Okay, I understand what's going on. This problem is confusing. That's the bottom line. That's what's going on. What's happening is, this is the rated current of the motor. So to find, and that was calculated in part A, which was not actually used anywhere, right? It was not actually entered anywhere in here. But how was this found? This is what's called the rated current of the motor. In this problem statement, it says that this motor is rated at this voltage. This is the power it consumes when the rated voltage is applied. And this is the power factor it operates at its full power. So at that operating condition, at the rated operating condition, at the rated voltage, you can calculate the current. And that's what was done here. We took the rated power divided by the power factor, so that's the S, divided by the voltage, divided by the square root of 3, will give me the line current.
Okay, that makes sense.
That's the rated value. In this problem, the motor is not operated at the rated voltage because we have a voltage drop due to the feeder. So the resulting current here is slightly lower than the rated value because we apply slightly lower voltage.
Okay,
Yep.
that makes sense. Thank you.
So the solution is confusing, but we didn't ask for this, right, in the problem.
No, yeah, that wasn't requested. It was just a
Just
value to solve for others.
Yep. Okay. Anything else we want to go through?
Do you have any tips?
Any tips?
Yeah.
Always think about if your solution makes sense. So go back to the problem statement and think about, okay, is this value what I would expect to see? Good ways to check or if the values make sense, is to do it in different ways to draw the phasor diagram. So if I look at any circuit, I can always draw for any node. If I sum up these three phasors, their sum should be 0. And then same thing if I have a loop with a voltage source and a bunch of impedances. If I sum the voltage, in other words KCL and KVL, the total sum should be 0, and I can see that on the phasor diagram. So fairly easily, if I draw the phasors, I don't even have to, be very precise. And I did that wrong. The arrow should be here. So this plus this plus this should be 0, and then same for the voltage. So that's a good check. Power triangles are always a good check to draw out. And then, always check what lagging is. I should say I lags voltage. Lagging I lags V, and Z is some R plus JX. There should be a plus sign here, and then leading. And of course, this is inductive. And then leading is I leads V, and Z, you should get a minus here. And this is capacity. So those are good checks at the end of a problem. I think those are the big ones. And then again, if you're getting some really strange numbers, then you're, or if you're deep into complex calculations, think back, is there an easier way to approach the problem? And then again, if you have the time, it's always good to do it in 2 different ways, and you should get the same result. All right.
Thank you.
No problem. Okay.
Thank you. Who's tabling on that?
You got here just in time. Is there anything on going to be on the test? Maybe a surprise? Or is it just basically going to be these same kind of problems?
It's going to be these same kind of problems. It's going to be AC circuit analysis, single phase. You can expect something with power factor correction, and you should expect a 3-phase problem.
Phasor diagrams?
Yeah.
Drawing phasor diagrams?
Yep.
Do you want us to always draw it like going back to itself, or